Chapter 12, Simple Regression. In this chapter, let's talk about the visual displays and correlation analysis. We'll then work on simple regression, regression terminology, ordinary least squares formulas, test for significance, analysis of variance for the overall fit, and confidence and prediction intervals for Y. And the optional materials are violation of assumptions, unusual observations, and other regression problems. The last three will not be covered in your test. It's just for your knowledge, for your information only. Okay. Let's start with the visual displays and correlation analysis. We touched upon correlation briefly before when we draw the scatter plot chart. Okay. About the visual displays, we can begin with the analysis of bivariate data. What is bivariate data? That is a data set that has two variables, and we can do a scatter plot on that. A scatter plot displays each observed data pair x and y as a dot on an xy grid. It indicates visually the strength of the relationship between the two variables. Okay. And if you remember, we do have a correlation coefficient that is used, R that's used to measure the degree of linearity in the relationship between x and y. Okay. And R, the correlation coefficient, is calculated by, this is the sum of xi minus its mean times yi minus its mean. And the multiplied result is summed over from y equals 1 to n, and in the denominator you have two square roots. The first one is xi minus x bar squared, then summed, times the square root of that, times yi minus y bar squared, then summed, then square rooted the radical of that. And that ratio here is the R, or correlation coefficient. By definition, mathematically speaking, the R can only be between +1 and -1. If R is 0, it indicates no linear relationship. And we can actually rewrite this equation as the sum of squares. We can call this xi minus x bar sum square of x2, right? Sum square of xi minus x squared, sum of sum ssxx, sum of square yy is yi minus y bar squared. That's right here. This is here, and xy equals xi minus x bar times yi minus y bar summed. Right? Then correlation coefficient equals ssxy over square root of this times square root of this. Okay. Now, we have also looked at this before in correlation analysis. If a trend is like this one, we say that it's a strong positive correlation. It's strong because they're the dots are aligned on the line very closely, and it's positive because it goes up. When x goes up, y goes up as well. In this case, the R equals, or is close to 0.1, +1. In this case, it's 0.9. Okay? When in a situation like this, we call it strong negative correlation. It's also strongly correlated, but the direction is negative because as y increases, y goes down, right? Go this way. So the R is close to -1, or it is 0.9. -0.9 in this case. When R is 0.5, around +0.5 or -0.5, we call it the weak positive or weak negative correlation. When R is 0, we call it then there's no correlation, or sometimes it could be a nonlinear relationship that also gives the R of 0. Okay, so the R signifies the strength of the linearity. Now, how do we test for this correlation? Right? We can test using it in testing the if rho. This Greek letter is rho. That is R is an estimate of population correlation coefficient rho. Right? This rho is the population correlation coefficient. So how do we test for this? First, we need to state the hypothesis. determine whether you're using a 1 or 2 tail test and the level of significance, alpha. Let's say if you use a 2 tail test, the null hypothesis is rho is 0, and H1 is null, rho does not equal 0. Okay? And then you specify the decision rule. For degree of freedom of nu, this little Greek letter here is pronounced nu. Nu is n minus 2. And look up the critical value of t in the appendix D, then we can calculate. Right? We'll work on some real questions, problems when we do the review questions. Step 3, you calculate the test statistics. Right. The test statistic in this case, the t calculated test that is r with the correlation coefficient times square root of n minus 2 over 1 minus r squared. That's your test statistic. And then you make a decision. If the sample correlation coefficient R exceeds the critical value of R alpha at the alpha level, then we reject null. If using the t statistic method, we reject H null if t is larger than t alpha, or if the p value is less than alpha, just like when we do our ANOVA analysis variance. Right? Test for significance equivalently, you can calculate the critical value for the correlation coefficient using this. R critical equals T alpha over square root of T alpha squared plus n minus 2. This method gives a benchmark for the correlation coefficient. However, there's no p-value and it's inflexible if you change your mind about alpha. There is a quick rule for significance, a quick test for significance of correlation at R.05. That is, R, the absolute value of R is larger than 2 over the square root of n. Let's say, for example, if n is 25, then using the quick rule, then the quick R critical is 0.4. Square root of 25 is 5, 2 over 5 give you 0.4. The actual R critical is 0.396. You can see it's pretty close to each other. For n equals 50, the calculated quick R is 2.283. Yeah, the actual one is 2.279. And 100, 2.2 and 0.196. 200, 0.141 and 0.1339. So you can use a quick test, right, if you need to. Now let's go let's start with the simple regression. Now, what is simple regression? Simple regression analyzes the relationship between two variables. It specifies one dependent variable, that's the response variable, and one independent variable, that's the predictor variable. This hypothesized relationship here will be a linear. In other words, it forms a line. Okay? So the unknown parameters are beta 0, which is the intercept, and beta 1 is the slope. Basically, we want, using group of data, we want to establish a line, a linear line that best represents the two variables. And assume the model of a linear relationship is this. We assume the model yi here, yi equals beta 0, the intercept, plus the beta 1, the slope, times xi, plus an error term for all the observations. The error term is not observable. It's assumed normally distributed with a mean of 0 and standard deviation of sigma. Okay. The fit model used to predict the expected value of y for a given value of x is y hat. This is the fitted model equals b0 times plus b1 x1 xi. Okay. The fitted coefficients are b0, that's the estimated intercept, and b1 is the estimated slope. And the residual is ei, or residual is the y hat, the predicted value, the fitted value, minus the actual value. So the residuals may be used to estimate the sigma, the standard deviation of the errors. How do we do this? We actually use regression using ordinary least squares method. Right? The ordinary least squares method estimates the slope and intercept of the regression line so that the residuals are small. or the smallest. The sum of residues equals 0. That is the actual y observation minus fitted model, predicted one value, added up, which they should add up to 0. Because sometimes you may have a positive one, sometimes you may have a negative, right? Then the sum of them is 0. And the sum of squared residue is SSE, sum of square error. SSE is yi times the y hat predicted value squared, summed, and equals, you plug in the y hat, that's b0 minus b1 x1. So that's SSE. Kind of similar to the concept in NOVA. Right? The OLS, ordinary least square estimator for the slope, is b1 equals that. Xi minus x bar times yi minus y bar that multiplied and then summed and divided by xi minus x bar squared and summed. Or this is actually SSXY, sum of square xy. This is the sum of square xx. And then once you have the slope, the intercept at OLS estimator for the intercept is simply y bar minus b1 times x1. So if you have a b0 and b1, you have the fitted line. Okay? Now, how do we assess the fit? How do we know the fit is good? Right? We want to explain the total variation in y around its mean. The sum square total for total sum squares, SST, just like before. So SST equals individual y value minus its y bar, the mean, okay, and squared and summed. The regression sum squared is the explained variation. This is from the regression predicted value from the regression minus y bar. Right? This part we call the sum of square regression, SSR. This is the part that's the variation that's explained or predicted by our regression model. Okay? Of course, there is, the unexplained part, unexplained variation in y. That's the sum of square error sum of squares, SSE. That's yi minus y hat squared. Predict, right? If the fit is good, the SSE will be relatively small compared to SST. In a perfect fit, is indicated by SSE equals 0. Okay? The magnitude of SSE depends on n and on the units of measurement. Okay? N is number of samples, observations. Let's introduce a new term called the coefficient of determination. Coefficient of determination, or capital R square here, is a measure of the relative fit based on a comparison of SSR and SST. Right? Basically, SSR over SST is your R squared, or coefficient of determination. And it also equals 1 minus SSE over SST, because we know R equals what? So SST minus SSE. So these two equations are equivalent. And by definition, coefficient determination, or capital R squared, is between 0 and 1. Okay? Often expressed as a percentage, and R squared equals 1 indicates a perfect fit. Okay? In bivariate regression, that was two variables, R squared capital and R squared lowercase r are the same. R squared is meaningful. In regression, we use that to say what percentage of the variation is explained by a model. Of course, you can come up with a model. We want to explain as much as possible the variations in the dependent variable. Okay? Standard error of regression. The standard error, SYX, is an overall measure of a model fit. Thus, SYX is defined as the square root of SSE over n minus 2. If the fitted model's predictions are perfect, SSE is 0, and this is 0, then the standard error is 0. That's a small SYX indicates a better fit. This is used to construct confidence intervals, as we'll see just a minute. Right? The magnitude of SYX depends on the unit of measurement of y and on the data magnitude. Okay? The standard error of the slope. And the slope of the curve of the line is SSE over n minus 2, the standard error, right? Standard error for the intercept is SYX, the standard error slope, times n1 over n x squared xi minus s bar squared and sum. Okay. I do not expect you to memorize all those equations, but just need to know where to find it, because our test is going to be open book, open notes. Okay. We can also construct confidence intervals for slope and intercept. Just like before, we have the slope and intercept, but what is the confidence interval? The beta 1 for slope, for the confidence interval for the true slope is between here, this, and that. B1 is the slope minus the t, and times the standard error of B1. And then the minus that, this is the lower end of the interval, and this is the upper end of the interval. We can also construct a confidence interval for the true intercept, beta 0. That's this and that. Okay. You can use Excel, Minitab, MaxStat, or other technology to compute these intervals and do hypothesis tests relating to their linear regression. Okay. Hypothesis test for significance. If beta 1 is 0, then we know that's the slope. Then x cannot influence y. Right? The y is independent of x. And then the regression model collapses to a constant beta 0 plus random error. This is the initial model. If beta 1 is 0, this item will be 0. Right? This is 0. And then yi equals just beta 0 plus ei. That's the error. Right? The hypotheses to be tested are for the coefficient of slope. This is the hypothesis test. This is the test statistic. For the intercept, this is the test, and this is test statistic. Okay. A t-test is used with a nu of n minus 2 degree of freedom to test the statistics for the slope and intercept. And the slope, the t, calculated t, is this, b1 minus 0 over as standard error of SB1. Intercept is TB0 or minus 0 over SB0. Okay. Then the n minus 2 is obtained from appendix D of Excel for given alpha. We can reject null if t is larger than t alpha or the p-value is less than alpha. When assessing the overall fit, we can do an analysis of variance here. Then we can look at the variance and decompose it, right, to explain variation in the dependent variable around mean. We use this formula: yi minus y bar equals yi minus y hat, the predicted value, plus predicted value minus y bar with the mean. If you open the brackets, you see these two cancels each other. It's simply this minus that, or it's this one. So this equation holds true. This same decomposition for the sum square is just like that, just like when we did in our analysis of variance. That's the sum of square here equals this plus that. And this is meaningful in that the first one, the sum of square total, and this one is actually our sum of square error. And this one is actually our sum square regression. So it's just very similar to ANOVA. So the total variation on the mean, SST, equals unexplained or error of some SSE plus explained by the regression SSR. SST equals SSE plus SSR. Okay? And the F statistic for the overall fit is similar to ANOVA. It's MSR over MSE. Or MSR is SSR over its degree of freedom, that's 1. SSE over its degree of freedom, n minus 2. Therefore, you get n minus 2 over times SSR over SSE. That gives you calculated F statistic. For given sample size, a large F statistic indicates a better fit. If H no, if F1F calculated is larger than 1 and minus 2 degree of freedom, then we reject null. We can get the F from appendix F for given significance level of alpha. or if p-value is less than alpha, just like before. Okay? Now, how to construct the interval estimate for y, the dependent variable? The regression line is an estimate of the conditional mean of y. An interval estimate is used to show a range of likely values of the point estimate. The confidence interval for the conditional mean of y is this. This is the interval upper limit minus indicate the lower limit. Okay? And the prediction interval for the individual one value is this. The prediction intervals are wider than the confidence intervals because individual y values vary more than the mean of y. Okay. And from this point on, the materials from this point on will not be covered in your test, will not be included in your test. This is just for information, for your knowledge only. Okay, if you're interested in studying further, right? There's a quick rule for confidence and prediction intervals. Quick confidence interval for the mean, you can use this equation to calculate. Quick prediction interval for the individual y, you can use this equation to calculate. Okay? And there are some assumptions in the regression. Right? The first one is that the errors are normally distributed. The second, errors have constant variance, that they are what we call homostatistic. The errors are also independent, that they are non-autocorrelated. Right? If they are dependent, then we call it autocorrelated. Right? So the error is unobservable. Right? And the residues EI from the fitted regression gives clues about the violation of this assumption. Non-normal errors. Non-normality of errors is a mild violation, since the regression parameter estimates B0 and B1 and their variances remain unbiased and consistent. Confidence intervals for the parameters may be untrustworthy because normality assumption is used to justify the student t's distribution. A large sample size would compensate, and an outlier could pose a serious problems. Okay? There is a normal probability plot. The normal probability plot tests the assumption. Right? The errors are normally distributed, or errors are not normally distributed. If H0 is true, the residual probability plot should be linear. Okay? This is just kind of linear. One can also display the histogram for the residues to see if it's linear. Okay? What to do about non-normality? If there is a non-normally distributed, what do we do? And in violation of assumptions. First, you can trim outliers only if they clearly are mistakes, and you can increase the sample size if possible. We'll try a logarithm transformation of both in x and y. You can see if that works. So, what if it's non-constant variance, or we call it heterostatic errors? The ideal condition is if the error's magnitude is constant, that is, errors are homostatistic, then heterostatic errors increase or decrease with x. And in the most common form of heterostaticity, the variance of the estimators are likely to be understated. This results in overstated t-statistic and artificially narrow confidence intervals. Okay. How do you test for heterostaticity? You can plot the residues against x. Ideally, there's no pattern in the residues moving from left to right, like in this case. Right? There's no heterostaticity. Right? If there's a fan-out pattern, this is the fan-out pattern, or this is a fan-in pattern. The fan-out pattern of increasing residual variance is the most common pattern indicating a heterostaticity that exists. Okay? Now, what to do about the heterostaticity? You can transform x and y, for example, by taking the logarithms. Although it can widen the confidence intervals for the coefficients, heterostaticity does not bias the estimates. Autocorrelated errors. Autocorrelation is a pattern of non-independent errors. The errors are not independent. In time series regression, each residue E should be independent of its predecessors before, right? but if not, it's autocorrelated. Autocorrelated errors, in the first order autocorrelation, ET is correlated with ET minus 1, the one before that. The estimated variance of the ordinary least square estimators are biased, resulting in confidence intervals that are too narrow, therefore overstating the model's fit. Runs for test run tests. You can run tests for autocorrelation. In the runs test, count the number of residues sign reversals. That is, how often does the residue cross zero center line. If the pattern is random, the number of sign changes should be n over 2. Fewer than n over 2 would suggest positive autocorrelation. More than n over 2 would suggest negative autocorrelation. Okay? You can do a Durbin-Watson test for autocorrelation under this hypothesis. H0 is errors are non-autocorrelated, and H1 is errors are autocorrelated. The Durbin-Watson test statistic is this, DW. Okay? The Durbin-Watson statistic will range from 0 to 4. If it's less than 2, it indicates a positive autocorrelation. With the DW is 2, it suggests no autocorrelation. That's the ideal situation. If DW is larger than 2, it suggests a negative autocorrelation. Okay? What to do about autocorrelation? You can transform both variables using the method of first differences, in which both variables are redefined as changes. Okay? You can changes xi changes the previous period, and the delta xt, and then y delta yt. You can transform that. Although it can widen the confidence interval for the coefficients, autocorrelation does not bias the estimates. Unusual observations. Sometimes we have unusual observations. You can let's talk in standardized residues. You can use Excel, Minitab, Megastat, or other technologies to compute standardized residues. If the absolute value of any standardized residue is at least 2, then it is classified as unusual. Okay? Unusual values. The standardized residue is at least 2. And the high leverage statistic indicates the observation is far from the mean of X. And these observations are influential because they are at the end of the lever. Right? It's high leverage. And the leverage of observation I is denoted as HI. And leverage and influence, a leverage that exceeds 3 over n is considered unusual. Okay? And studentized deleted residues. Studentized deleted residues are another way to identify unusual observations. A studentized deleted residue whose absolute value is 2 or more may be considered unusual. A studentized deleted residue whose absolute value is 2 or more is considered an outlier. Okay. Outliers, other problems in regression. Outliers may be caused by an error in recording the data or impossible data, an observation that has been influenced by an unspecified lurking variable that should have been controlled by, but it wasn't. Right? To fix the problem, you can delete the observation, or you can delete the data, or formulate a multiple regression model that includes the lurking variable. Okay? Model specification. If a relevant predictor has been omitted, then the model is misspecified. Model misspecification. You can then use multiple regression instead of bivariate regression. This is beyond the scope of this class. Right? You condition the data. Well, conditioned data values are of the same general order of magnitude. You conditioned data have unusually large or small data values and can cause loss of regression accuracy or awkward estimates. Okay, you conditioned data, you can avoid mixing magnitudes by adjusting the magnitude of your data before running the regression. And there's also the issue of a spurious correlation. In a spurious correlation, two variables appear related because of the way they are defined. This problem is called the size effect of the problem, or the problem of totals. Okay? Model form and variable transforms. right? Variable transforms. Sometimes a nonlinear model is a better fit than the linear model. It happens. And then Excel offers many model forms. Variables may be transformed using logarithm or exponential functions in order to provide a better fit. Log transformations reduce heterostaticity. Nonlinear models may be difficult to interpret. But these all, again, all beyond the scope of this class. This is just for your knowledge only. Okay, if you're interested. Again, as I said, the test, your final test, will only cover the front part of this chapter. Now, this concludes Chapter 12, Regression Analysis.